For 1,000s of years, human communication was limited by the horizon. If you wanted to share a visual event, you had to draw it, paint it, or describe it in written words. From the early cave paintings in 30,000 BC to the sophisticated messenger networks of the Roman Empire in 100 AD, transmitting information was physically bound to the speed of one person, one horse, or one ship. The idea of seeing something as it happened across vast distances was relegated to the realm of magic, crystal balls, and mythology. However, the 19th century AD brought a fundamental shift in how humanity understood the natural world, specifically electricity and magnetism. The invention of the telegraph in the 1830s AD proved that information could be encoded into electrical pulses and sent instantly over copper wires. Then, in 1876 AD, the telephone proved that the complex, continuous waves of human sound could be converted into electrical signals, sent across a wire, and translated back into sound. If the human voice could travel through a wire, scientists and dreamers began to ask a seemingly impossible question. Could we do the same thing with moving images? Could we build a machine that acts as an electronic eye, allowing us to see across the world in real time? The first major breakthrough toward this dream did not come from an inventor trying to build a television, but from a serendipitous discovery involving underwater telegraph cables. In 1873 AD, an English telegraph engineer named Willoughby Smith was testing materials for the transatlantic telegraph cable. He was using a chemical element called selenium. Smith noticed something strange. The electrical resistance of the selenium rods changed depending on how much light was shining on them. When exposed to bright light, the selenium conducted electricity much better than when it was in the dark. This property, known as photoconductivity, was the missing link. It proved that light could be converted directly into an electrical signal. This one discovery ignited the imaginations of inventors worldwide. If you could measure the light of an image and convert it into electricity, you could theoretically send that electricity through a wire to a receiver that would convert it back into light. However, an image is not one single point of light. It is a complex field of varying brightness and color. To send an image through one single wire, it had to be broken down into pieces, sent one by one, and reassembled on the other side so quickly that the human eye would not notice the process. This concept is called scanning. In 1884-81, 23-year-old university student in Germany named Paul Julius Nipkow came up with the first practical method for scanning an image. Nipkow designed a spinning disc with a spiral pattern of small holes punched near its edge. If you placed this disc between a brightly lit object and a light-sensitive selenium cell and spun the disc rapidly, each hole would sweep across one single line of the image, letting light pass through to the selenium. Because the holes were arranged in a spiral, the first hole scanned the top line, the second hole scanned the next line down, and so on until the entire image was scanned. The selenium cell would convert the varying light intensity of each line into a fluctuating electrical current. On the receiving end, a synchronized spinning disc would place a fluctuating light source in front of the viewer, recreating the image line by line. Nipkow patented his invention, known as the Nipkow disc, in 1885 AD. However, he never built a working model because the light-sensitive materials and amplifiers of the 1880s AD were simply not sensitive or powerful enough to make it work. For tens of years, the concept of television languished as a theoretical novelty. It was not until the early 1920s AD that the components needed to make it a reality finally existed. The invention of the vacuum tube amplifier allowed weak electrical signals to be boosted to usable levels. Enter John Logie Baird, a Scottish engineer with a history of failed business ventures and poor health. In 1923 AD, living in poverty in the seaside town of Hastings, England, Baird decided to build a working television system based on Nipkow's spinning disc concept. His early prototypes were built from whatever scrap materials he could find. He used an old hat box, one pair of scissors, some darning needles, bicycle light lenses, and sealing wax to construct his mechanical scanner. He even used a motor from an electric fan to spin his crude cardboard discs. The device was incredibly loud, dangerous, and prone to flying apart at high speeds. Because the discs spun so rapidly, the metal and cardboard would warp and shatter, sending shrapnel flying across his small bedroom laboratory. But Baird was relentless. By 1924, A.D. Baird managed to transmit the flickering silhouette of a Maltese cross over a distance of 10 feet. He moved to a small laboratory in London and continued to refine his apparatus. The challenge was increasing the sensitivity of the photoelectric cells to capture the subtle variations of a human face rather than just stark black and white silhouettes. To get enough light for his scanner, Baird had to use massive, incredibly hot lamps that would physically singe the hair and skin of anyone sitting in front of them. He primarily used a ventriloquist dummy named Stooky Bill for his experiments because a human subject would have melted under the intense heat. Finally, on October 2, 1925, A.D. Baird achieved a breakthrough. He successfully transmitted an image of Stooky Bill with recognizable grayscale halftones. The face was composed of just 30 lines and refreshed 5 times per second, producing a blurry, flickering image, but it was undeniably a face. Excited, Baird ran downstairs and grabbed one 20-year-old office boy named William Tainton, paying him 2 shillings and 6 pence to sit in front of the scorching lights. Tainton became the first human being to be televised. On January 26, 1926 AD, Baird gave the first public demonstration of his mechanical television to members of the Royal Institution and a reporter from the Times newspaper. The demonstration proved that moving images could be transmitted instantly, sparking a global race to commercialize the technology. Concurrently in the United States, an inventor named Charles Francis Jenkins was working on a similar mechanical system. In 1925 AD, Jenkins transmitted the silhouette image of a toy windmill in motion over a distance of 5 miles. Jenkins called his invention radiovision, and by 1928 AD, he had opened the first television broadcasting station in the United States, transmitting silhouette programs to a handful of amateur enthusiasts who built their own receivers. The mechanical television era had officially begun. The British Broadcasting Corporation, or BBC, even began broadcasting Baird's 30-line television programs in 1929 AD. Viewers had to buy a Baird televisor, a large wooden cabinet with a tiny screen about the size of a postage stamp, magnified by a thick glass lens. The picture was dim, orange, and flickered violently. Despite these early successes, mechanical television had a fatal flaw. The spinning discs could only spin so fast and have so many holes before they became impossibly large and physically unstable. One 30-line image was enough to recognize a face in close-up, but it was entirely inadequate for broadcasting complex scenes, sports, or sweeping landscapes. To achieve a high-definition picture, the image would need to be scanned into 100s of lines, requiring the disc to spin at 1,000s of revolutions per minute. It was a mechanical dead end. The future of television would require a system with absolutely 0 moving parts, using something that could move at the speed of light. The electron? The foundation for electronic television was laid in 1897 AD by the German physicist Carl Ferdinand Braun, who invented the cathode ray tube. A cathode ray tube is a vacuum tube in which a beam of electrons is fired at a phosphorescent screen, causing a spot on the screen to glow. By using magnetic or electric fields, the electron beam could be steered up, down, left, and right at lightning speed. In 1907, a Russian scientist named Boris Rosing realized that a cathode ray tube could be used as a television receiver. Rosing successfully transmitted crude geometric shapes to a cathode ray tube, becoming the first person to use electronic methods to display a television image. However, Rosing still used a mechanical system to scan the image on the transmitting end. The ultimate goal was an entirely electronic system, one camera that used electrons to scan the image, and one receiver that used electrons to display it. The solution to the all-electronic television camera came from the most unlikely of places. In 1921, one 14-year-old farm boy named Philo Farnsworth was plowing a potato field in Rigby. Idaho Farnsworth was an avid reader of science magazines, finding them in the attic of his family's new home. He had read about the limitations of mechanical television and the spinning Nipkow discs. As he guided the horses back and forth across the field, cutting straight parallel furrows into the earth, he had an epiphany. He realized that a television picture could be created in the exact same way. An electron beam could sweep across an image line by line, back and forth, from top to bottom, exactly like plowing a field. This electron beam could read the light variations and translate them into electrical signals almost instantly. Farnsworth sketched his idea for an image dissector tube for his high school chemistry teacher, Justin Tolman. This diagram, drawn by a teenager on a chalkboard in 1922 AD, held the fundamental blueprint for modern electronic television. Farnsworth was a brilliant, self-taught genius. By the time he was 21 years old in 1927 AD, he had secured private funding and set up a laboratory in San Francisco. On September 7, 1927 AD, Farnsworth successfully transmitted the first fully electronic television image, one simple straight line painted on a piece of glass. When the glass was rotated 90 degrees, the line on the receiver rotated as well, proving the system worked. In 1929 AD, Farnsworth transmitted the first fully electronic image of a human being. His wife, Pem Farnsworth, holding a cigarette so viewers could see the smoke rising, proving the image was live. His system had absolutely zero spinning disks, zero moving parts, and could scan images at unprecedented speeds, offering the promise of crystal-clear, high-definition television, while Farnsworth was working in his small, independent lab in California. One massive corporate giant was preparing to enter the television race. The Radio Corporation of America, or RCA, was the most powerful broadcasting and electronics company in the world, led by the ruthless and visionary David Sarnoff. Sarnoff had built an empire on radio, and he knew that television was the next frontier. He was determined that RCA would not just participate in the television revolution, but that RCA would completely control it, own all the patents, and reap all the profits. Sarnoff's primary weapon in this war was Vladimir Zworykin, a Russian-born physicist who had been a student of Boris Rosing. Zworykin had immigrated to the United States after the Russian Revolution and had gone to work for Westinghouse and later RCA. In 1923 AD, Zworykin applied for a patent for a fully electronic television camera tube he called the iconoscope. Zworykin's early iconoscope was deeply flawed and could not produce a recognizable image. But RCA poured massive resources, eventually totaling more than $50 million, into perfecting his designs. By the early 1930s, Zworykin and his team of hundreds of engineers at RCA had developed a highly sensitive and practical electronic television camera. The problem for RCA was that Philo Farnsworth had already patented the fundamental concept of an electronic television system in 1927 AD. Farnsworth's patent covered the basic idea of using an electron beam to scan an image line by line. Even though RCA's iconoscope was a different design from Farnsworth's image dissector, it still relied on the fundamental principle that Farnsworth had patented. David Sarnoff could not stand the idea of paying royalties to one 20-something-year-old independent inventor from Idaho. Sarnoff initially tried to buy Farnsworth out. In 1931 AD, Sarnoff visited Farnsworth's laboratory and offered $100,000 for the patents and a job at RCA. Farnsworth, wanting to build his own company, refused the offer. He stated that he would only license his patents in exchange for continuous royalties. Sarnoff was furious. RCA immediately unleashed an army of corporate lawyers, initiating a brutal, grueling series of patent interference lawsuits against Farnsworth. RCA argued that Zworykin's 1923 AD patent application preceded Farnsworth's 1927 AD success. Even though Zworykin had never built a working model at that time, the legal battle dragged on for nearly 10 years, draining Farnsworth's finances and severely damaging his physical and mental health. However, in a dramatic turning point, Farnsworth's old high school chemistry teacher was called to testify. The teacher produced the original sketches that the 14-year-old Farnsworth had drawn on the chalkboard back in 1922 AD. This proved beyond a shadow of a doubt that Farnsworth had conceived the idea of electronic scanning first. In 1939 AD, the Patent Office definitively ruled in Farnsworth's favor. RCA, the invincible corporate giant, was forced to capitulate and sign a licensing agreement, agreeing to pay Farnsworth continuous royalties for every television set RCA manufactured. It was the first time in RCA's history that the company had to pay royalties to an outside inventor. With the legal battle settled, RCA was ready to unveil television to the world. On April 30, 1939 AD, David Sarnoff stood in front of a television camera at the New York World's Fair. His speech was broadcast to 300 to 400 television receivers scattered around the New York area. President Franklin D. Roosevelt also spoke at the opening ceremony, becoming the first president of the United States to be televised. RCA began manufacturing and selling television sets to the public with screens ranging from 5 to 12 inches in size. One typical set cost around $600, a massive sum of money at the end of the Great Depression, equivalent to $1,000s of dollars today. Programming was limited to 3 to 4 hours a day, consisting of boxing matches, cooking demonstrations, and newsreels. The age of television seemed poised to explode, but geopolitics intervened. In December 1941 AD, the United States entered World War II. Almost overnight, the production of commercial television sets and broadcasting equipment was halted. The factories that had been building consumer televisions were retooled to build radar systems, radios, and communication equipment for the military. The engineers and scientists who had been developing television were drafted into the war effort. For long years, the development of television was frozen in time. However, this forced hiatus had a silver lining. The massive technological advancements made in electronics, cathode ray tubes, and high-frequency transmission during the war provided the perfect foundation for one massive technological leap once peace was declared. Before the war had fully halted progress, a crucial step was taken to ensure the future of the medium. In 1941 AD, the National Television System Committee, or NTSC, established a unified standard for television broadcasting in the United States. They set the standard at 525 lines of resolution and 30 frames per second. This was a critical decision because it meant that a television set built by any manufacturer would be able to receive broadcasts from any network. Without this standardization, the market would have fractured into incompatible systems, severely stunting the growth of the industry. The NTSC standard would remain the backbone of American television for the next 70 years. When World War II ended in 1945 AD, the pent-up consumer demand and the newly established technological infrastructure resulted in an explosion of television, ownership that is unprecedented in the history of consumer electronics. In 1946 AD, there were only about 6,000 television sets in American homes. By 1951 AD, there were 12 million sets. By 1955 AD, exactly 50% of all homes in the United States had a television. The flickering screen rapidly became the center of the American living room, fundamentally altering family dynamics, evening routines, and the consumption of news and entertainment. Radio networks transitioned their most popular programs and stars, like Milton Berle and Lucille Ball, over to the visual medium. The golden age of television had begun, bringing the entire world into the domestic sphere in glorious high-contrast black and white. But even as black and white television was conquering the world, engineers were already fighting the next great war, the race for color television. The desire for color had existed since the mechanical era. John Logie Baird had actually demonstrated a crude mechanical color television system as early as 1928 AD, using a spinning disc with spirals of red, green, and blue filters. In the 1940s AD, the Columbia Broadcasting System, or CBS, led by engineer Peter Goldmark, developed a highly advanced version of this mechanical color system. The CBS system used an electronic camera and a cathode ray tube display, but it placed a massive, rapidly spinning wheel of red, blue, and green filters in front of the screen. The system produced beautiful, vibrant colors, but it had one massive flaw. It was entirely incompatible with the 1 millions of black and white NTSC televisions already sitting in living rooms. One black and white set attempting to pick up a CBS color broadcast would just display scrambled, unwatchable noise. Despite this incompatibility, the Federal Communications Commission, or FCC, approved the CBS system as the national color standard in 1950 AD, largely because it was the only system that actually worked at the time. David Sarnoff and RCA were enraged. They argued that it was fundamentally unfair to render 1 million seconds of existing black and white sets obsolete. Sarnoff ordered his engineers at RCA to work around the clock, throwing millions of dollars into developing a fully electronic color system that would be backward compatible. One RCA color broadcast needed to display in full color on a new color set, but it also had to display perfectly in black and white on an older existing set. Sarnoff established a massive research facility, referred to as the Princeton Laboratories, and tasked hundreds of the brightest minds in physics and engineering with solving this seemingly impossible puzzle. The engineering challenge was monumental. It required transmitting 3 separate color signals, red, green, and blue, and compressing them into the same narrow slice of bandwidth used for one single black and white signal. RCA engineers, including the brilliant George Brown, utilized complex mathematical techniques to interleave the color information into the existing broadcast frequencies. They also developed the shadow-masked cathode ray tube, a display that featured 100,000 south of tiny phosphor dots that glowed red, green, and blue when struck by 3 separate electron beams. By 1953 AD, RCA successfully demonstrated their electronic-compatible color system. It was a technological masterpiece. The FCC realized their mistake, reversed their earlier decision, and adopted the RCA-compatible system as the new NTSC color standard in December 1953. AD, the first national color broadcast was the Tournament of Roses Parade on January 1, 1954. AD, however, color television sets were incredibly expensive, and it took another 10 years before color programming became the norm. By the late 1960s, AD color televisions began outselling black and white models, painting the living rooms of the world in vibrant electronic hues. As the picture quality improved, the reach of television expanded outward, breaking the bonds of terrestrial geography. In the early days, television signals could only travel in one straight line, meaning they were blocked by mountains and the curvature of the Earth. Broadcast range was limited to a radius of about 50 miles from the transmission tower. To send a live signal across a continent, expensive microwave relay towers or coaxial cables had to be laid point to point. Transmitting live television across an ocean was physically impossible. That changed on July 10, 1962 AD, with the launch of Telstar 1. The world's first active communications satellite, built by Bell Labs and launched by NASA, Telstar 1 received television signals from the ground, amplified them, and beamed them back down to another continent. On July 23, 1962 AD, Telstar relayed the first live transatlantic television broadcast between the United States and Europe, featuring a press conference by President John F. Kennedy. The era of global live television had arrived. The ultimate demonstration of this global connectivity occurred on July 20, 1969 AD, when an estimated 600 million people, representing a significant portion of the human race, simultaneously watched the ghostly, slow-scan television images of Neil Armstrong taking the first steps on the moon. To achieve this, Westinghouse engineers had to design one special television camera that could withstand the extreme temperatures and vacuum of space. Using 1,500 line resolution format that was beamed to Earth, converted to the 525 line NTSC standard, and then distributed globally. Television had truly unified the planet in one single, shared visual experience. In the 1970s AD and 1980s AD, the method of delivering television to the home underwent a revolution. Since the 1940s AD, television had been dominated by 3 or 4 massive broadcast networks that beamed their signals through the air to rooftop antennas. However, the rise of cable television, which delivered signals directly through physical coaxial cables, shattered this monopoly. Cable could carry tens and eventually 100s of channels without worrying about broadcast spectrum limits. This led to the creation of dedicated 24-hour news networks, sports channels, and premium movie networks, fragmenting the mass audience into specialized niches. Concurrently, the invention of the video cassette recorder, or VCR, allowed users to record programs and watch them on their own schedule, breaking the strict temporal tyranny of the network broadcast grid. As the 20th century AD drew to a close, the fundamental architecture of the television signal was rebuilt from the ground up. For 70 years, television had relied on analog waves, continuous fluctuations of voltage that were prone to static, ghosting, and interference. The late 1990s AD saw the beginning of the digital transition. Analog signals were replaced by digital broadcasting, encoding the picture and sound into binary code. Streams of 1 south and 0 south. Digital television allowed for perfect, flawless transmission without static. More importantly, it enabled the leap to high-definition television, or HDTV. While the old NTSC standard offered 525 lines of resolution, HDTV offered 1080 lines in a wider cinematic aspect ratio.
The picture quality was vastly superior, offering a level of detail that rivaled 35mm motion picture film.